Hello and welcome to this short vignette on outliers and influence in linear regression. You need to be careful when building linear regression models and look for influential outliers. Not all outliers are influential though. So in this video we will track the influence of a single observation on the coefficients of our model. So the solid red dot here is the observation we're going to follow, and watch how the regression line changes as the point moves around the window. Let's see, bring up our video here. So when the point moves up and around this area here, we see that there's a strong influence on the slope of the line, particularly when it strays from where the regression line would be without this observation. The most influential observations will be those that are far from the mean. The regression line will pass through the mean of x and the mean of y, and the regression line will tend to pivot around that point. This point here that passes through the mean of x and the mean of y. Now, when we move this observation to the mean of x, then we'll see much less of an influence of this data point on the regression line. As the sample size increases, the influence will drop off even more. We can see very slight perturbation of the intercept, but the line is moving up and down slightly as our observation changes, but the slope isn't changing at all. Now, when we move our observation along the trend line, we see absolutely no change in the slope or the intercept. Observations in the middle of our cloud of points, especially when they're right on top of the trend line, are going to not have much influence on the regression coefficients. In fact, if it's on the trend line, it will have no influence over the regression line or the predicted outcomes. So we're going to add two outliers to our data set, and we're going to look at those throughout the rest of this vignette. One of them here is at the mean of x, and that we're labeling as observation number 101. And one of them over here is at the mean of y, and we're labeling that as observation 102. As we saw in that short video in the previous slide, we are going to expect this point at the mean of x to have very little influence on the regression line. But this point over here at the mean of y should have more leverage. And that's because when we do our least squares algorithm, we are trying to minimize the distance, this vertical distance, to the trend line. And so here we are pulling against all of these observations, while here this is going to have more leverage. It's like a teeter-totter. It's a seesaw. It's going to pull on that line with more influence. So we can use the outlier test function from the CAR package to check our model for outliers. This will show us up to 10 outliers in our model. That is residuals that are larger than expected, either positive or negative. And here we see that observation 101, that's our point above the line at the mean of x, is the only outlier that's showing up. The unadjusted p-value is a measure of how far the residual is from zero, but because we'll expect some observations to be further from zero, especially as we get larger sample sizes, we're also given a Bonferroni corrected p-value that takes the total number of observations into account. If we increase the threshold, though, the default is 0.05. If we increase the threshold, the cutoff, we see that observation 102 also shows up on the list. It's the next one to show up on the list. So when we look at this output, We're surprised that observation 101 is that far away from the rest of the data. Are we surprised? Yes, because it's further away than we would expect, even accounting for all of the observations that we've made. But should we be surprised with how far away observation 102 is? Perhaps not. But there is more to outliers than just how far away they are from the regression line. More to outliers than that residual value, that error term. So remember that some outliers affect the coefficients in our model more than others. The influence plot, also from the CAR package, would give us a nice picture of what outliers we need to worry about. On the y-axis, we have the studentized residuals. That is, we rescale the model residuals so that they have a standard deviation of 1. On the x-axis, we have the hat values. This is a measure of how much the predicted values change when we compare the two models. One observation, one model with the observation, and one model without. And the bubble size is a measure called Cook's distance. That's a measure of how much the model coefficients change as a result of the observation. So the hat values represent the change in the predicted values, and the Cook's distance is a measure of how much the model coefficients change. So they're related but not exactly the same. And we are given the observations down here that are most extreme and that we may want to pay attention to. So our big question is, how much influence does each single observation have on the model output? It appears that, as expected, observation 101 has very little influence on either the predicted values or the model coefficients. So it is an outlier. The residual is way out here, but it does not have much influence. Observation 94 has a relatively high influence on the model coefficients, but not so much influence on the actual predicted values from the model. The Cook's distance is pretty small here. So the bubble size is very, very small. Observation 102, on the other hand, has a relatively high influence on the model coefficients and on the predicted values. Its influence on the predicted values is on the order of 8 times the influence of observation 101, and its leverage over the coefficients is about 40 times greater than observation 101. You can see that by looking at these values down here. So now if we go back to our figure here, so this shows our outliers that we've added in. Note that this point here is observation number 94. It is right on the line, so the residual is very small. But without that data point, the regression line will drop noticeably. You can think of this as, again, as a seesaw. These two most extreme values of x, here and here, are both pulling on the seesaw, and the fulcrum is at the mean of x and y, here in the middle. So when observation 94 is not included, these 3 data points here allow the seesaw to, or the regression line, to drop, and this pulls up that regression line significantly over here on the left side. In fact, these 3 lines are pulling the regression line in the same direction, because as this moves down, that moves up. So that's why observation 94 has such high leverage over the model coefficients, because it's pulling this end here back up. I think in the end, we'd probably want to remove observation 102 from the data set, this one here. If we did decide to do that, we would need to mention it in our discussion of the results. Observation 101 is less troubling, primarily because it doesn't seem to have much influence. So while it looks a little odd out here all by itself, it isn't really changing any of our conclusions. So in summary, the residuals are the difference between the observed and predicted value of the outcome for a specific observation. The studentized residuals, which are shown here on the y-axis of our influence plot, are the residuals rescaled so that they have a variance of 1, so that when we look at that influence plot, we always have 0 at the center. We have 2 standard deviations out here, and we have the same spread always when we look at that figure. The hat values that are on our x-axis provide a measure of the amount of influence each data point has on the outcome predictions. So how much do those predicted values change if you exclude a specific observation from the model? That's what this is measuring. And then Cook's distance provides a measure of the leverage of each observation on the regression coefficients. It answers the question, how much would my model coefficients change if I excluded this observation from the model? So again, the hat values and Cook's distance are related, but they're not exactly the same thing. These are helpful measures to have when deciding what to do about outliers in your data. The outlier test and influence plot functions can be helpful in visualizing the influence and diagnosing possible problems with your data.